how's everything? How was the last lecture?
Good.
Was it good?
Kind of good.
All right. So I believe was last lecture we are done with the analysis of beams and frames and trusses on SAP2000. And today I'm gonna assign our first homework on SAP2000. And today we are gonna shift to the fifth system, which is the SLAB system. And I believe this is kind of like your first practical, or like I would say real life project, because the thing is, everything that we have done right now is a separate element in a structure, beams or one truss. Usually the structure is multiple components, is columns, beams, slab system, and that's what we are gonna have here today. This imagine was made, this is like a condominium, and this is the typical floor plan of the condominium. This condominium has this floor plan, maybe 4 apartments. It has an elevator in the middle, and basically it is gonna serve, let me show you, actually I believe I have an architecture for this one. Yeah, here. All right, so for example, usually the architecture is something like this. You have, we're going to solve this right now. You are having a condominium, and that's actually our job as a structural engineer. We get drawings from the architecture, and we try to convert this architecture drawing into structural drawing. Architecture usually have walls, have like it tells you where's the doors, where's the ducts, where's the voids, where's the elevator. Everything is going to be here. But this doesn't mean that everything here is a structural system. Our structural system is beams, columns, walls, slabs. That's it. That's all what we have in our drawings. The architecture can have a lot of stuff. Can show you, actually this doesn't show you the furniture. Sometimes he has the furniture inside there. This is a bedroom, so it tells you, oh, there's a bed here, there's a closet here. But this is kind of a simplified architecture. So let's imagine this architecture. Definitely, if you have a building, it should be like, definitely there's a stairs. Elevator is something kind of optional. So this has stairs and elevator. So once you get from the stairs, there's 2 apartments. Apartment here, that's really huge. 1 bedroom, 2, 3, 4, 5. So this is kind of like half symmetric, 2 symmetric apartments, and I don't care. All what I care about, I want to develop a structural system that can hold this system and be stable. Okay, that's all what I care about as a structural engineer. And in the same time, I want to choose a system that is not going to mess up with this architecture drawing. Like for example, sometimes the architecture doesn't give you a hypothetical locations of the columns. Let you decide where the column is, but sometimes he gives you, oh, I would assume to have columns at these locations. This is, I believe, my guess. Sometimes it's like, oh, I believe I need more columns. Oh, you have a big span. So, or like for example, let's say we talked about the solid slab system. Do you guys remember? We have multiple systems. We have something, I believe I explained it before. You have solid slab system, and you have solid slab, and you have flat slab. These are one of the most used slab systems in condominiums. Either solid or either slab. Waffle slab, I rarely see them. Post tension slab and just a few applications. Sometimes, yeah, I start seeing a lot of post tension slabs. So let's say you have post tension slab. There's something called hollow core slab. But the main 2 systems is these 2 systems. And actually this and this and this is kind of extension from the flat slab system. So the solid slab system is any system that has for example, the load transfer to beams, and then the beams transfer, the load transfer from our loads transfer to slab, and from slab to beams, and beams to columns. Flat slab system, the slab transfer the load to the columns right away. And we talked about this before. Usually in the flat slab system, you have the slab something like this, and the column is punching the slab right away. But if you have a solid slab system, you have a beam, a very deep beam, and the slab is something here. If we make it 3D, it's gonna be something like this, and this beam is something here, something like that. Okay. So basically, and I have a column like this. So, and maybe let's say there's another beam that way, and this is our slab system. So basically, this slab transfer the load to the beam, and the beam transfer the load to the column, and the column transfer the load to the foundation, and the foundation transfer the load to the soil. Here in the flat slab system, the slab transferred the load to the column right away, and I told you there's a very, very important check when we have this slab system. We have to check if this column is gonna bunch the slab or not. It's called bunching the check. And in solid slab system, there's no bunching the check because there's beams that are very deep that can transfer the load. We talked about this before. So, and let me tell you, the solid slab system is way cheaper than the flat slab system. Way, way cheaper. However, this can cost more in labor, more than this one, because the thing is you need labor to make forms for these beams. So you have to, this beam is 70 or 2 feet depth. This beam is 3 feet depth. So you have to have a labor so that they can form forms for these beams. But the flat slab system is just one level. No ups, no downs. All the elevations are the same, and it's only one thing. So the labor here is it cheaper, but the cost of the material is less because it's only, I'm not saying it's less, no, it's still, the labor is cheaper, but the material is expensive because you pour concrete, like let's say you are gonna use a slab here, the thickness usually in the solid slab system is around, let's say 12 centimeter. But here, you use very thick slab, around 30 centimeter. So almost the double or more than the double of this. So that's a lot of concrete that you are gonna put here. Let me tell you, this system is very common in the Middle East. This system is very common here in the US. You guys know why? Because the labor here is expensive. So you save a lot of money in labor, but in the Middle East, the labor isn't cheap. Or I believe also in many countries, okay? So, but we still do the same systems. Also, post-tension slab system is kind of an extension of the flat slab system. But the thing is, I told you that the idea is like, here is, let's say this is the flat slab system. When you put a cable and you apply, let's say you are gonna put a cable here and you apply a tension here on this cable, and when you bore the concrete, you lift the tension, so this cable basically apply load on this beam that way. And when you apply load on this beam that way, basically this beam is gonna be something like this. So when you put the original loads that comes from the floor system, is gonna bring the beam back to something like this. So basically, you are resisting the loads on the beam by counter moment before and like make the beam take more loads. So basically you are saying you on something. Alright, so this is my slab system. You put the loads, my beam is gonna be something like this. So you say, how much is this deformation? This deformation is 3 centimeter. So what about if I apply a post-tension force that give this beam a camber 3 centimeter before the load? So once you put the load, the beam or the slab is gonna be straight. So you apply a load on the system that can counter the loads that are coming. And actually we'll see this. Do you guys know that trucks, the big trucks, usually look at these trucks when they are moving on the road, you will find that it's the main system of the truck is an I-beam in the middle. And this I-beam has a camber like this. So when this truck get loaded with whatever the cargo load that is gonna have, this beam is gonna take the straight level again. Look at all these trucks, the one that are not closed, the one that are like, yeah. So you will find it's something like this. It's not straight. But when you load it, it's gonna take the original or the flat position. Anyway, so as a structural engineer, when I get a plan like this and I start to design it, first I have to decide where are the columns. If the architecture is giving me the columns, I might use them, or I might add more, or I might take less, it depends. And if I'm gonna do a solid slab system, I have to be careful with the location of the beams. Like here, I can put a beam that can be supported by this wall and this column. But I can't put a beam that comes from here to here, so you don't stay in the living room and you find like a beam coming. You need to see a whole flat thing. So the better engineer you are, the more that you make the structural system more appealing. So like you don't want to have a beam in the middle of the room that cuts the room into half until you try to make it in an architecture, like in a beautiful architecture way. Some people would use that. Anyway. But if you have a flat slab system, so you don't worry about the beams. The whole thing is gonna be flat, and you are gonna make the slab right away resting on the column. So I don't care, or I don't have to worry about the location of the beams, and that is the beauty of flat slab system. It's just one slab, there's no beams, and all the slab is just loading on the columns right away. But everything comes with a coast. All right, so this is my architecture plan, and the thing is, what I have to do, I have to delete all the walls inside and just leave the columns and the walls, and because these are structural components. So once I delete everything in the middle, leaving the columns and the walls, it's gonna be something like this. So basically, that is my structural plan. It's a very simple one. All I have to describe, what is the size of this column, what is the dimension of these walls, what is the dimension of these walls, and I can make a circle in the middle and put what is the slab thickness. That's mostly our structural drawing. But this is just geometry. We have to provide another one for reinforcement in the X direction, another one in the reinforcement in the Y direction. That's usually studying in reinforced concrete. But let's see how we are gonna do analysis for that one. All right, from my perspective, I believe here the spans here is like around 5 meter. This one is 7 meter and 7 meter, which is regular spans for flat slab system. Flat slab system can go up to 10 meter in span. You'll tell me, oh, how about if it's 12 or it's 15? It can go 12 and 15, but the slab thickness is gonna be huge. And at some point, the flat slab system is not gonna be economical when you exceed a specific span limit. So we usually use flat slab system around 6 to 10 meter. If you exceeded that span, you have to find something else. You have to use panel beam, maybe you have to go to post tension or roller core slab. Roller core slab, I believe some of them are post tension. So post tension is really good. It can go you up to like 12, and sometimes we use it in the smallest spans, like 7 meters, just to make it economical. Because let's say if you use 30 centimeter without post tension, you can bring this 30 centimeter to 15 centimeter or 16 centimeter with post tension. Can you imagine you are just gonna put a few cables or a bunch of cables inside your slab system? Is gonna decrease the cost by 50%. Because you bring the slab system from 30 to 15 in the whole square footage area of your plan. So that's why I believe most of the construction companies and most of the design firms, they start going with the post tension slab. All right, so let's see how we can solve this slab system on SAP2000. We're gonna do the same thing like we did before. We have to start by defining the materials, defining the loads, and start drawing the geometry. And once we draw the geometry, we apply the location of the support. But before I do this, I want to tell you something. This is a typical floor plan in a 10-story building, okay? So what we do exactly when we design a 10-story building, if it's all the floors are typical, we take one story, like this one, and then do something called 2D analysis. What is the 2D analysis? I don't do analysis for the whole 10 stories. I do analysis for one story. And the one story is gonna give me what is the reaction of each one of these columns and what is the reaction of each one of these walls. And using these reactions, I do preliminary design for the columns. Because the thing is, the column in the versus story, and actually this is story number 1. The columns in the versus story hold 10 stories like this, right? So if your reaction here is 10 ton, what is the total reaction of the 10 stories? It's 10 by 10, 100 ton. Because this is only one story gives you 10 ton load. So if you have 10 stories, that's 100 ton. Then you design the column and find the dimension. Once you find the dimension, right now you can draw the 3D of this building and make the whole 10 story. Because the way that we're gonna do it right now, we don't know what is the dimension of this column. So in the 2D, we are just gonna put a hinge. And this hinge, once we get the reaction, we can design this column and get dimensions. Do you guys get that? So at this point, I don't have any dimension for this wall. I only have the length of the wall, but not the thickness. Because I say, oh, this wall is gonna be like 2.7 meters or something. But the thickness, I can control it based on how much load that this wall is gonna get. Same thing the column, I don't know. This might be 40 by 40 or 50 by 50 rectangular column. But how can I know that? I'm gonna put an inch here, and then I will get the reaction. The reaction for this story is gonna be 10 ton. And this story have another 9 stories above, so 10 by 10 is 100 ton. Let's design this column. And once we design this column, we can know the dimension. So that's what happened in every building's design. We design 2D, 1 story, get preliminary dimension for the slab, for the columns, for the walls. And why I'm saying preliminary dimension? Because at some point, once we do this 3D analysis of the building and apply seismic load that makes moment in the X of the column and moment in the Y, these dimensions might change because right now I'm only designed for gravity loads. But once I apply wind and seismic, all these might change, either reinforcement or either concrete dimensions. So step 1, I make the 2D plan, get reactions, and then get bending moments on the slabs and the beams, and do preliminary design. And by the way, the design of the beams and the slab is gonna be the same. It's never gonna change. Once you are done with the 1 story, that's it. The other 10 stories doesn't impact the slab and the beam because the slab and the beam are very, I would say, they are local. Like it doesn't matter what are the stories above and down. It just matters. It's a local system. It is designed based on the local loads. The things that might change is the wall and the columns because the wall and the columns are holding the whole building. So everything above them is going to affect them. Okay? But the load in the versus story on the slab is not going to affect the slab system in the tensor story. And the load of this beam, it doesn't affect the beam system in the tensor story. So all what happens here, the slab system transfers the load to the beam like this or like this, and then the beam transfers to the columns and the walls, and that's it. All right, so let's see how we can do this on SAP2000. I'm gonna get back here as we learned before. I will start by File, New Model. I define the dimensions, and I'm gonna start with grids only, as we learned from before. So let's see what we're gonna do with the grids. I'm gonna zoom in here. So I have the dimension here is 7, and all these are 5s, and there's 7 at the end, okay? And this wall is 2.7 meters. Let's actually measure the dimension. Distance.
Nice. Thank you. Do we have this AutoCAD file?
Yeah, I'm gonna send it to you. All right, 2.75. This wall. And here, same thing. This is 755, and I have this core. Let me check the dimensions here. would say 1 meter down and 1 meter up, and this wall is like 3 meters from here to here. Alright, so let's draw the grids. So I want to right now to find out how many grids should I make in the x direction and how many grids should I make in y direction. Can you guys tell me? Okay, I'm gonna make a grid here to draw this beam, and I want a grid here to know the end of the wall at 2.75, and then a grid after 7 and 5, and I want a grid in the middle. So this is 7, 5 is gonna be 12, and this is 5, so the middle is gonna be 2.5 plus 12 is gonna be 14.5, and then a grid here, and a grid here, and a grid here, and a grid here. That's for the x direction. For the y direction, I need one here, 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 this, like this, right? That's the grids that I want, so I can draw this thing. Okay, I'm gonna go here, so I need, all right, 1, 2, 3, 4, 5, oh, sorry.
5, 6, 7, 8, 9.
6, 7, 8, 9. So I need 9 grids in the x direction. How many in the y? Sorry. I'm gonna put x is 9. Let's get back here. We're gonna need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 in the y direction. I don't have any z right now, so I'm gonna make the z is 1. And the distance, this is the thing, the distance right now are not the same. Some are 7, some are 13. So what I'm gonna do, I'm gonna keep them and adjust them manually, and let's see how we can do that. So I'm gonna keep everything the way it is, and I'm gonna ask to start from the origin 0, 0, and 0, and I'm gonna say okay. So SAP2000 is gonna do the distances that were there, and all of them are equal. So let's see how we can adjust them manually. You make a right click on the screen, and it's say here, edit grid data. So, and then you say, I want to modify this grid data. Once you hit modify, all the distance in the x and the y direction are going to show up. And by the way, they are measured from 0. Like, they are not distances, they are coordinates. So the first grid is at 0, the second grid is at 5. If you guys remember, I want the second grid to be at 2.75, so I can draw this wall. And then I have 7. 7 plus 5 is 12. 12 plus 2.5 is 14.5. And plus 2.5 again is going to be 17. And then I'm going to have plus 5 is going to be 22. 22 plus, okay, this is 2.75. Gonna be 29 minus 2.75 is gonna be 26.25.
Yeah. All right. Yeah.
All right.
26.
So let's put them. I have, as far as I remember, I have 2.75, and then I have 7. 7 plus 5, 12. 12 plus 2.5, 14.5, and then I have 17. And then 22, and I know that the last one, 22 plus 7 is 29, and I subtract 2.7 from the 29 is going to be 26.25. All right, and how about the other direction? I have 0, 2.75, and 7. 12, 12 plus 1, 13, 13 plus 3, 16, 17, 17 plus 5, 22. Okay, get back here. So I have 0, 2.75, 7, 12, 13, 16, 17, 22, that is 29, and this is 26.25. and then I'm gonna hit OK. And OK. Alright, we did something wrong. Alright, let's get back and create data. Modify, let's see what did I do.
I think the X is correct. The Y is
Oh.
confused.
Oh, I put 48.
Oh, it's supposed to be 26.25.
That's supposed to be 29, and this one is supposed to be 26.25, right? Okay, now it's fixed. Alright, so I prepared the grids to start drawing, okay? But before I start drawing, by the way, I have some walls here, some walls here, and I have walls here. But before I start drawing, I want to define the materials, and I want to define the cross sections, materials of the concrete, because I'm going to use concrete. I want to define cross sections of the walls. Maybe not the walls. I want to define the beams and the slabs, because I'm going to represent the walls as hinges, because these are supports. I don't know exactly what is the dimension of the walls and the columns. Okay, but I'm gonna assume the beam. And by the way, I can assume the beam and slab system and see if my assumption, and that's actually what we do in design. When we do in design, the code tells you, based on the span, what is your preliminary assumption of the beam's dimension and the slab dimension. It is function in the span. All right, so let's start here by define materials. I'm gonna go to the material, and I'm gonna go to this one and modify, and see if I want to modify anything, like if you want to name it FCU30 or something, and then put all the things that you want to do, but I would rather use the same material here. So I would keep the material the way it is, and I'm gonna define load pattern. Oh, I forgot to record. Just 1 second.
But it's in PSI. Why are we using metric system?
That's a good point. I'm gonna tell you. Stop. All right, let's get back to the material. Define material and modify and show. All right, so you said it's a metric system, right? Why we have a 4,000 pound per square inch while all my units are in ton force meter? Focus. So this is just the name of the material. The name of the material. I can name it, as I said before, Omar, or whatever name that you want to say, or when I call it FCU. But everything here is in ton force meter. The weight per unit work, and the Young's modulus, and everything here. So it is just a name. So you can name it whatever you want, but usually when we name it with, this is basically the conversion of the unit. Like if you change the unit here, everything here is gonna be changed. So the name doesn't matter much. You can name it any name, any unique name that you want. And then, but the things that matters here, that these units must match the general units that you are using. Okay? All right. So I'm gonna keep it the way it is, and then I'm gonna say okay. I'm gonna get back to define load patterns. And here I'm gonna keep the unit load 1 because I don't want to calculate the own weight of the structure. I want the SAP2000 to calculate the own weight of the slab and the beam system. However, I'm gonna add a live load, and the live load I'm gonna make the own weight here 0 because I don't want SAP2000 to calculate the own weight 2 times. Because if you kept it 1, it's gonna calculate the own weight and put it in dead loads, and calculate the own weight and put it on in the live load. And then I'm gonna hit OK. So I define the loads. Let's go define the sections. I'm gonna define frame sections for the beams. So I'm gonna add a new property, and I'm gonna add concrete beams. And let's say I'm gonna make these concrete beams, I'm gonna name it B25 by 70 centimeter. And I'm gonna make the depth 0.7, and I'm gonna make this is 0.5, and I make sure that the material is 4,000 pounds per square inch. Concrete, I'm gonna hit OK. If you want to define the columns, just in case if we're gonna make this as a 3D, you can add new property and you can add rectangle, and you can name this column C1, for example, 50 by 50 centimeter, and I make sure that I have this 0.5, and I have this one also 0.5, and I'm gonna hit OK. If you want to define, for example, another column, let's say I'm gonna add a copy of this one. I'm gonna change its name. I'm gonna name it C2, and for example, let's make it C2 25 by 80 centimeter, and I'm gonna make the depths, for example, 0.8, and this one 0.25. I'm gonna hit OK. So I define all the cross sections, and I'm gonna hit OK. So right now I define the beams and the columns. Let's go to the slab. I'm gonna define section, and I'm gonna go to area section. And as I told you before, there's multiple area sections that you can choose from. You can choose shell, you can choose plate, you can choose a solid. Actually, they don't have the membrane. But anyway, I believe the membrane is gonna show up when we go inside. So let's add shell as we agreed before, and add new section. And here, yeah, here it shows the type of the shell that you want. Do you want shell thin or thick, plates thin or thick, or a membrane? So usually I'm gonna go with shell thin because that's what we use with flat slab system. If you have a foundation that are very thick, or the flat slab system is really thick, like more than 0.5 meter or something, I would go with shell thick. So I'm gonna make a slab system of 30 centimeter. And I make sure, by the way, if you name it slab 30 centimeter, you still have to change the membrane thickness and the bending thickness. So why you have to put two thicknesses? So basically, the shell is kinda a membrane and plate at the same time. Do you guys remember? There's a membrane that can take loads in a specific direction, and there is a plate that can take loads in a different direction. So we said that the plate can have bending moment that way, right? That's the plate. The membrane take moment out of plane, like the shear wall. Loads is coming that way, and the shear walls is resisting the walls that way. Okay? So right now I picked shell. Shell has both the plate and the membrane. So basically it's asking me, what is the thickness of the slab that is effective in the membrane reaction? So like use the whole thickness. In the membrane reaction, act that way, so the full thickness is working with me. In bending, which is the plate action, I want also the full thickness. So basically they are both the same. Okay. And I would choose the material. I'm gonna keep the material concrete.
So for membrane, the thickness is height or is it width?
It's always the thickness, which is like if the wall, it's gonna be that one. If it's a slab, it's gonna be that one. The smallest thickness.
But so then, if membrane is vertical, means
The membrane is like you have the slab like this. It's like this. That's the wall.
So it means you're saying it's gonna be 30 centimeters wide
30 centimeter thickness. Yeah, that one.
if we design a membrane, but we're gonna design a slab, so it's gonna take the
Exactly.
bending.
So usually these things, it's kind of like this software deal with it as a matrix. Okay, like do you guys remember the degrees of freedom? The degrees of freedom for the plate and membrane were 12, but for the shell were 24. So basically, when you put the loads on the plate, the loads are gonna move the degrees of freedom of the 12, but there is nothing coming that triggers the other 12. So it's gonna make the other ones the zeros, and the other ones is gonna have numbers. Okay? So that's exactly what happened inside when you use shell for a system that is gonna get only plate loads. Okay? Alright? So think about it like, oh, we are using shell for just safe, to be safe. Because sometimes I told you, you have a wall, and the wall usually designed, because this is the thing what happens with walls. We design the wall to take loads in the strong direction. What is the strong direction of this wall? That way, right? This wall is like weak in that direction. You give it load that way, it's gonna bend that way. but it's stiff in that way. You guys know that? Because the stiffness is much
The
bigger
moment of inertia.
in the moment of inertia, right? So that's what we do, but is this what happened? Like this wall is only gonna take load in this direction? No. There's some loads that are gonna come in the other direction and make bending on the wall. So this wall is gonna bend that way and that way. That way, maybe when torsion happens, and it happens. So that's why when we have wall inside the system, it's better to make it chill, because definitely this wall is gonna have a moment that way, and a moment that way, and maybe a moment that way.
And the slab is similar?
If what? No, it's gonna happen whatever, because this only happens when you have a seismic load. Like if you don't have a seismic load, all the loads is gonna go down. There is no bending that way, and there's no bending that way. This wall is gonna act like all the loads are coming that way.
For a slab, you can also have.
That's true. If you
Is
have
that why we're putting 0.3 for the membrane, or?
that can happen. Well, we usually put it just like as an effective thickness of the slab. But the slab, if there's something is called rigid and flexible membrane. So usually when we assume a slab is a rigid, that means the slab cannot do this action. But if it's a flexible membrane, so it can make that action. And right now the membrane is effective in that case. So that's why we always model the systems as shell, because they can take membrane and the bending load, or membrane and plate action. Okay, so getting back here to where we at, I'm gonna hit OK after putting the slab thickness. So right now, the only last member that I need to define is the wall section. So right now, I'm not gonna draw any wall. In the future, I will. In the 2D, I'm not drawing any wall, but I'm gonna define it here, and I'm gonna say it's a still shell thin, and I'm gonna say it's wall, let's say 30 centimeter too. And I'm gonna also still keep this is at 30.3, and this is 0.3, and I'm gonna use the same material of the concrete. So I have all the sections, all the loads, and everything is defined. So right now is the moment where I need to draw everything. So you're gonna start by drawing the walls and drawing the columns and then draw the slab. But what I'm gonna do, I'm gonna draw the slab first, because it's gonna help me to draw the walls and the columns much easier. So how I'm gonna draw the slab? I'm gonna draw the slab here. You can come to draw, and there's something here, it's called draw bully area, which is the slab, or draw rectangular area, it's still a slab, or quick draw an area. Let's see the difference. All these are outside here. You can use them here. I'm gonna go outside. I can click this one, and here when I open this, it's asking me what cross section that you want to use when you draw the slab. The slab 30 centimeter or something else, because you can choose between multiple things. So if you look here, you will find the wall, but right now I'm drawing a slab. So if you pick the one that has the bully area, so you have to draw the slab one point by point. Can you see? Like this, and once I'm done, I can escape. Let me try again. Somehow it didn't draw the slab. Okay, let's try the rectangle one.
Yeah, I think you have to.
Okay, draw with rectangle. I don't know why it didn't draw with the other one. So this is one big slab system here. I just want to make sure that I didn't draw multiple slabs on top of each other. Oh, it says here one area. That means it's only one slab. When I select it down there, it says one area. So that's also one way to do it. Or I can delete this, and there's something it's called the quick draw. Quick draw, you have to be in the 2D, but the thing is you have to click on each one by one. Can you see what I'm doing? It drew a slab in each area, bounded by a grid system. Okay, the easiest way to do that, I want to tell you something. When we do finite element analysis, and that's what all the software, this is the method that all software is using. SAP2000, ETABS, any software, I believe most of the software out there, they are using the method of finite element. What is the method of finite element? What does it do? It's an empirical method. And what I mean by empirical, like let's say this is the slab system, and this slab system has a support here, and support here, and support here, and support here. And it has a bunch of loads. What's supposed to happen to this system when it has this load? It's supposed to have a deflection, it's supposed to have bending. So the finite element method, if you take this class, and I believe Dr. Mahrabi teach this course, I'm not sure if you guys took it. So finite elements solve the structure at the point. Like if you have a joint here, and a joint here, and a joint here, so these joints is where the finite element make the solution. And then it take the average of all the points to come up with an average bending moment. So the thing is, let's say finite element try to solve for the deflection here, and the deflection here, and the deflection here, and the deflection here. What is the deflection here?
0.
You have a hang, and here 0 and 0. So basically, once you have the slab system, let's say this is 5 meter by 5 meter, and you make the mesh size of the slab 1 mesh, and this mesh or this slab is 5 meter by 5 meter. So basically, the finite element is going to solve for 0 deflection, and the deflection that you are going to get in the middle is going to be 0. So that is one of the, let's say, the drawbacks of finite element. That is empirical method that takes average based on the number of joints that you have. So if you want to make your solution better, you have to divide this into more elements. So basically, when you get the deflection here and the deflection here, it takes average, 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 and then you are going to show more deflection. If you want to make your solution better, you have to divide this into more elements. And the smaller the elements that you have, the more accurate is your solution. However, if you increase the number of elements massively, the software can take forever until it's solved, because it is going to take more time to solve at each joint. And then it needs to take the average of each one of these joints. You guys got that? So the acceptable mesh size when we do finite element analysis is around 0.5 meter. So that's what we mostly use when we solve for gravity loads. So what I'm going to do, I want to draw the whole slab system of the structure and divide them in a way that I can get accurate solution. And this way is going to be by making the mesh size equal to 0.5 meter. So let's see how we can do that. What I'm going to do, first, I'm going to draw one slab for the whole structure. Oh, sorry. Oh, why it didn't? Okay, make sure it's a slab 30 centimeter, and then I'm gonna stop it here. All right, so this is one slab, and then what I'm gonna do next, I'm gonna divide this slab with the grid system. I will go to edit, and then you will find something is called edit area and divide area, and then I'm gonna go to divide area based on points or area edges, and I'm gonna do it divide with the intersection of visible straight grid lines with the area edges, and I'm gonna say okay. So why did I do that? I did that because if this is your slab system and you have a column in the middle, if you don't have an intersection of joints at this column, like let's say you have a column here, or let's say you have another column here, this column is not gonna feel the slab. The column needs to be attached to a joint. If the column is not attached to a joint, the slab will never feel it, because that is how the finite element is working. So I divided the slab system at the intersection of the grid lines because I know at each grid there is either a column or a wall. And I need this grid system to have a point at this column or the wall. Okay? If you try, when you go home, do the same thing and draw a column here. you will find that the slab having a deflection, like not feeling the column, like it's going up and down. So that's really, really important when we do finite element analysis. So let's say that you have a column here. What you should do, we usually drag this point and drag it here. Move it here. There's a way that we can do this on SAP2000. All right, so I did divided the slab system that way so I can draw hinges at the location of the column. So right now I can assign, like I know that there is a columns at these four corners. I'm gonna select them. I think I had a column here. I didn't have column here.
Drag and draw like a rectangle to select them, it also selects the slab area. Does that matter? Or?
Yeah, actually it's the joint in the slab. What we did here, like this division, this is a slab, and this is a slab. So basically, you generate a specific point on the slab that can drop the load at the column. If this joint, because the thing is, it's all about these joints. It doesn't matter what is inside here. It's all about these joints where all the calculations happen.
Like if I do this, to select the points, it selects this.
Yeah, that's not, that's your question. So no, it doesn't matter because when we assign hinges only assign at joints. Okay, so, oh yeah, I'm selecting here. Okay, you guys tell me if I missed anything. I believe that's all the columns that we had. Let's look at the plan. I had all columns around the core, and oh yeah, I don't have a column here because I have a wall on these sides, so maybe I'll go back, take these out, because I have walls at this area. Okay, I'm gonna go here and I'm gonna add a sign joint.
I think you missed some.
Where?
So at the bottom, you have where the walls should be.
The middle ones.
Here?
To the left.
Here?
Right. No, right to the right. That one. Take that one off, and then on the other
Oh
side.
yeah, because there's wall, okay. By the way, if I left them, it's okay because we are gonna assign some stuff here later, and you're gonna find out. But let's keep it that way for now. I'm gonna assign joint, restraint, and I'm gonna make hinges, and I'm gonna say okay. So right now we have hinges at these locations. So what about the wall? The problem with the wall, if I wanna model it, the thing is the column is just at one point, but the wall is linear. So what I'm gonna do, I'm gonna make a beam like here, and I'm gonna make this beam really, really stiff. And add, imagine with me that you have a wall here. If it's a column, the column is just holding at one point. But if it's a wall, it's holding the whole area. So this slab is feeling a very stiff element here, which is the wall, that it's like, imagine with me that the wall, can you see this beam? It's just a 7.7 or 1 meter. 1 meter, for example. The wall is the whole story height. So that's what the slab is seeing. A very stiff beam that has a depth with the whole story height. So I can make a section and make the stiffness of this section infinity or very huge and assign hinges at every point of this section. And I'm gonna show you right now how we can do that. But let me make, define a section, frame section, and let's say this frame section is the beam, the same beam, and I'm gonna add a copy. And I'm gonna name, let's name it F section 1, the same name that the software developed. And I'm gonna set modifier, and I can multiply these modifiers by like 10. Like I'm multiplying the stiffness of this beam by 10. actually, let's actually not playing the weight or the mass. Let's keep the mass the same. Just playing in the stiffness. And I'm gonna say, okay. So why I did this section? Because right now I'm gonna draw a beam and I'm gonna pick up this section. And by the way, this section is temporary for now. And I'm gonna draw at the location of the walls. I'm gonna draw one here, and I'm gonna draw one here. This section is a beam section that is really, really stiff, and we are gonna find out how we can make this section act like a wall. All what I need from this is I want a reaction. Like I want a reaction at the supports that are here. And I believe I have a core here. Did I miss any walls? Oh, I had one. I think I got them all. All right. So that's all the walls that I have. And I'm not gonna assign supports right now on the wall because I'm gonna tell you why. But what I'm gonna do right now, I can run this model. I can put the loads, I can actually assign the supports at the end of this walls, and I can run the model. But the thing is, this model is not gonna be that accurate, because can you imagine, this is the mesh size. Can you imagine how big it is? 5 by 5. Bounded by a column, so you need more joints here to improve the accuracy. So you need to divide this into more small elements so that the software can calculate the deformation and calculate the bending moments and the shear force and everything as inside and increase the accuracy inside the slab. But you know what? Let's run this model without doing this and see what's gonna happen. Let's see how much time we have. Okay, I'm gonna assign supports here so that you can imagine what I'm talking about. And here. Assign, join.
You missed one.
Did I miss one?
Yeah,
Alright.
on the right button.
Top left.
Join, constraint. All right, so let's run this slab under its own weight. I didn't save the analysis. I'm not gonna run model. And I'm gonna say right now, it's gonna ask me to save the analysis. So let's save it as slab 30 centimeter. Say okay. It's not going to take that much time when you run the analysis with respect to if you divided this into smaller mesh. So the analysis will be fast. And let's see how's the dead load, because right now this is that it's under its own weight, the dead load. So let's see how this is going to look like. All right, I'm going to show the deformed shape in the 3D. So let's say I want to show the deformed shape, and I want to show the deformed shape under the dead load, and I'm going to say, okay, look how the slab look like. It feels like a broken, I'm not sure if you guys can see it. Can you see? It's like a broken in the middle and making like this, but this is not the actual deformation. The actual deformation should be like curved. You see? So that doesn't make sense. Why? Because basically he's taking an average between this and this, and it's only one point in the middle that can move. And all the point is dragged. So the thing is, we need to add more points so that we can make this shape more like realistic. So by the way, in the showing the deformation, you can show contours. Like you can say here, I want to draw contours in the Z direction, because this is where the deformation is happening. And it's going to show you how's the contours look like. Where is the maximum deformation? By the way, the maximum deformation usually is around this area. But the thing is, this is not that much accurate because we didn't define the mesh in the right way. Okay? So let's see how we can improve the accuracy. I'm going to unlock the model and start dividing this into smaller mesh. So I'm going to select all the slab, I said Control A. When I said Control A, it selects everything. Slab, beams, frames, joints, everything. However, this doesn't matter right now because the loads or the things that I'm gonna do is just specific for the slab. So I'm gonna go to Edit, and I say Edit Area. So basically, it's gonna go, SAP2000 is gonna go to my selection and select only the area and apply the order that I'm gonna make only on the area sections that I have. And I'm gonna divide the area. I'm gonna tell SAP2000 that divide the area into objects of the maximum size, for example, 0.5 by 0.5. So SAP2000 is gonna divide these areas into a maximum area of 0.5 while maintaining the original division. Okay, so this doesn't mean that the areas is gonna be 5.5. The maximum is gonna be 5.5. But he's gonna divide it within here. Let's say this is 4.7, so he's gonna make, for example, the mesh size 0.4 or 0.3. Depends on how the areas look like. So, and then let's hit OK and see what's gonna happen. All right, look what happened now. The mesh size is really small, and I still have a joint at each column. And I want to do something for you. Okay, let's actually zoom, restore the full view. I don't know what happened here. Okay. Yeah, I want to do something. I want to put a hinge somewhere here. Like I'm gonna add a point. Let's click on the point here, and I'm gonna add a point here, and I'm gonna select this point. Let's select this point, and I'm gonna assign a hinge at this point. Joint, restraint, and I'm gonna put a hinge. All right, there's a hinge at a point that is not connected to the slab system. And see, let's see if the wall is gonna, if the slab is gonna feel this point or not. Okay, that's one thing. Other thing, I can put live load, but one thing we forgot to do, and I wish that we didn't forgot because right now it's messy a little bit. There's an elevator in this area, right?
Yeah.
Should we have a slab here or no?
No.
If there's a slab here, there's no way that the elevator is gonna go up and down. So usually, we have to delete this thing. And usually we put a coupling beam here. Like if we look at the drawing, there's a beam here. So let's put this beam because we forgot to draw this beam. So I'm gonna put, usually the coupling beam is much more heavier than the regular beam, but let's put beam 25 by this. So I put the beam, everything, and let's assign live load. I'm gonna select the whole slab system. And the thing is right now, the software only calculates the loads only calculates the own weight of the structure. However, there is weight that is not here, like for example, the flooring weight or the live load. So let's assign this. So I'm gonna hit assign, and I'm gonna assign something is called area loads, and this area loads is a uniform shell because all my loads are uniform on the whole square footage of the area. So I have a super dead load, which is the flooring load. So let's assume that the flooring load is 150 kilograms or 0.15 ton per meter square. And by the way, when I leave this load in the dead load, so basically he's gonna combine the flooring that I have with the own weight of the structure in the same dead load. If you wanna separate them, you have to create a new load pattern. Let's call it super dead or something. But right now, I'm gonna keep it that way, and I'm gonna hit OK. And all right, let's select the slab again, and I'm gonna assign the live load. I'm gonna go to area loads, uniform shell. I'm gonna change this from dead to live, and I'm gonna make the live load is 200 kilograms or 0.2 ton, and I'm gonna hit OK. By the way, all the green that you have here, basically SAP2000 wrote 0.2 at each shell area. 0.2, 0.2, 0.2, so that's why you have all this green. If you want to make sure of the loads that you put on your system, you can make zoom in view. Can you guys see? So he's writing the loads on this slab. The live load is 0 in the x, 0 in the y, and negative 0.2 in the z direction. You can right click on this shell, and you are gonna find all the assignment in this shell. You can find that the loads assignment. It has dead 0.15 and it has live load of 0.2 in the gravity direction. Alright, so I have all the load, so let's run this slab and see what we're gonna have. So I'm gonna run the analysis and I'm gonna hit run. It's gonna take more time right now because we have more elements. Oh, didn't take that much. Alright, the thing is, I can see the deformed shape right now, but there is a lot of stuff here that I don't want to show. So what I'm gonna do, you can click on this checkbox. Can you see this one? And I'm gonna ask SAP2000 only display sections. And general options. I'm not gonna show ages or reference lines. Let's say apply. See what's gonna happen. And I don't want to show the points because it's annoying. So I'm gonna let's put the restraints. Apply. These joints showed because we had.
What are you trying to do?
The thing is, I want to hide the points that are in the middle here. So I'm trying. Oh yeah, let's make it invisible. Okay, here we go. I'm gonna click on this view too, and let's make it invisible. All right. Because it was like I can't see very well when the software was showing me everything. So let's see. I'm gonna make zoom into the full view. Right. Can you see now how the deformed shape look like? It's a little bit heavy, but this is, can you see right now, you have more points, there's contours, and things are much more realistic and close to the real. Like you have here, this is the center of the slab system, where you have most of the biggest information. And let me actually close this view and get to that view. And actually you can play here with the visualization. Like for example, if you want to show general options and you want to show the sections, apply, ages, like something like this, so that you
can have more realistic view. And basically in this view, you can get closer to the maximum deflection and have your cruiser, and then you can check, like for example, here's the maximum deflection is 0.0025. But by the way, this is only due to the depth. If you want to check this, due to a combination, you can define load combination. For example, I can define combo 1. I'm gonna multiply the dead load, for example, by 1.4 as a scale factor, and live load by 1.6, and you can visualize the deformation due to the combination of dead and live load. And I'm gonna hit OK. So when you do this, you are gonna have deflection here, definitely much more. Which is 0.004, which is almost the double. I want to look for the column that I drew, and you guys remember where it was? So that, because the thing is, I draw a column somewhere here. It's, show the undeformed chain.
Well, it all looks symmetric.
It's below the, it's right there, it's right there, you just pass over that.
Right.
To the right.
To the right.
This
Right
one?
there, down.
Yeah.
Okay, let's zoom actually on this column. Let's see what's gonna happen there. And let's show the deformity chain. And let's say, okay.
Oh, because it doesn't consider.
Like, if there's a column here, it should have a blue like this. But it doesn't. Like, all the columns and all the support, it has blue. Here at that column, that means that the slab didn't feel it. And if we want to see this in, like, let's remove the contour lines. I'm gonna hit OK. And actually, let's remove the fill. Like, I'm not, let's go to the general option and get rid of that. Let's see if the column is there. Somehow we can't see it when we run the analysis. Here. Yeah, so when you run the analysis, it doesn't show because it doesn't contribute to the slab system. So it's basically, it's like a dummy column that doesn't do anything to your system. All right, I want to teach you how to extract some results here. So, I want to remove the slab. Let's make it by label. Let's remove the sections. Actually, let's remove the labels too. And I'm gonna get back to the general options. Let's fill the objects. And you can see the slab something like this. I'm gonna say I wanna see the XY. If you wanna see the 3D view, you can see the 3D view from here. By the way, if you wanna show the slab as a thickness, you can come here and say that to the general option that you wanna see an extruded view. Extruded view basically is going to show you how, but it's going to make the whole software is heavy. Like, can you see? It is. It's going to show you some thickness of the slabs and beam. And by the way, we forgot to put beam around the slab system. Like, we forgot to put it's called the marginal beam. If we want to put it, basically, you are going to come here to the beam section and you say that you want to draw the B 25 by 25 and you can start drawing your B all around, something like that. And let's get to the 3D. And right now you can see your structure in a 3D visualization. You can run your analysis again. All right.
shouldn't those be considered walls? Shouldn't they be?
Okay, look
Beams
at,
shouldn't be deflecting them.
what is your question again?
Why are the beams deflecting the arch?
Here,
Aren't those
Or here.
supposed to be walls?
Which one?
Yeah,
this is a beam, this is a
Those
real
are beams, those are not
Yeah, this is
walls.
beam, it's called like, when you have a building, a flat slab system, sometimes we put a marginal beam around the slab system, it's called marginal beam. But look at what happens here, this has deflection, doesn't have any deflection.
So,
Why? Because we put two supports this is acting like a wall, we made it to act that way. How? We put two supports at the start and the end, and we make that beam very, very stiff. So you barely have deformation at that beam. But if you wanna make this beam more acting like a wall, you pick all these joints and assign a hinge, like this joint and this joint and this joint, and assign hinges at all of them. So that's also another way, like you can pick a flexible beam and put hinges at all the points on this beam. So this is multiple ways to do it. Okay, so that's it for now. Next time we're gonna see how we can extract the results, like bending moment, shear force diagram, bending moment on the slab in the X and Y direction, and how we can convert this into a 10-story building. Okay? See you guys next time.
Wait.
Bye, Professor, thank you.
Thanks, have a good day.
Alors, c'est pas fini, mais voilà, ça va.